Thank you for attending our presentation on an IO separation model for formal verification of kernel implementations. I'm Miao Yu. The goal of the IO separation model is to authorize IO transfers to isolated applications and their drivers. An IO transfer can be informally viewed as an ordered association of one or more devices to one or more driver objects. For example, a USB device can transfer data to its associated buffer, and a GPU device can display its associated frame buffers of several isolated application drivers. An IO transfer is authorized if drivers cannot bypass or modify a device's association with its object or misconfigure the device to violate the associated read or write permissions. For example, if a device is associated with an object of a specific driver, then the driver cannot change that association to an object of a different driver or application. To be useful, the model is to be IO hardware, OS, and application isolation agnostic. This means that it must apply to all IO hardware designs, OS kernels, and application isolation mechanisms. Why is this a challenge? As I will show next, most IO hardware fails to authorize transfers. Most IO kernels aim to separate IO transfers, but fail to do so with any degree of implementation assurance. And most trusted execution environments provide some application isolation, but fail to separate the IO transfers of otherwise isolated applications. Many IO hardware designs fail to provide adequate transfer authorization. Thus, a malicious driver can manipulate its non-malicious device to bypass device-object association or read-write permissions. Some IO hardware provides no authorization at all. For example, a conventional PCI device can issue peer-to-peer transfers to another device without providing the sender device's ID. Thus, the sender device can spoof host controllers to access the target device of a driver in a different application, thereby violating driver application isolation. Some IO hardware provides only non-selective authorization. For example, IOMMUs authorize transfers at the granularity of PCIe to PCI bridges, but not for individual PCI devices underneath. Other hardware provides selective authorization, but OSs end up violating it to improve performance, as I'll show it in the next slide. Here we illustrate 4 attacks that violate IO separation when using inadequate IO hardware. Recall that conventional PCI devices can issue peer-to-peer transfers to other devices without providing the sender device's IDs. Because of this, a malicious driver I can configure device I to access device J without any authorization. This enables unauthorized direct transfers. Further, the write driver I can enable unauthorized indirect transfers. The write driver writes to device I as before, but configures it differently. The configuration enables P2P accesses from device I to H, which further enables P2P accesses from device H to J. This shows that only identifying the target device in the first P2P access is insufficient to prevent unauthorized indirect transfers. Next, recall that IOMMUs authorize transfers at the granularity of PCIe to PCI bridges, but not for the individual PCI devices underneath. Because of this, device I can access not only the red DMA memory, but also the green DMA memory. The IOMMU allows this access because it associates the transfer with the bridge, not individual PCI devices. The last example shows a selective authorization failure resulting from a performance optimization. Recall that IOMMUs separate DMA transfers selectively via different page tables, and to improve access performance, they must use IOTLBs, which must be cleared upon page table switches. However, commodity OSs defer IOTLB clearing to decrease switching time between different device transfers. For example, in the figure, this causes deferral of the green IOTLB entries deletion even after they are no longer used. So when a device moves to the red partition on demand, the red driver can still configure it to access green DMA memory via the undeleted IOTLB entry. In summary, these examples show that, first, address space separation is insufficient for IO transfer separation. And second, a malicious driver can violate IO transfer separation by manipulating its non-malicious device to bypass transfer authorization. Currently, many different OSs, IO kernels, and trusted execution environments provide application isolation. For example, a microhypervisor and a WinP kernel enforce on-demand IO separation for isolated applications and their USB devices. And separation kernels establish isolated partitions and statically allocate devices to these partitions. Commodity OS kernels enforce intra-OS protection to separate a DMA memory pool from a non-DMA memory pool. Then they transfer data to and from the separated pools to isolated applications. To ensure that our formal model is applicable to all IO hardware, kernels, and TEs, we use a layered modeling approach. The abstract model layer specifies key device and driver components and operations, formalizes the notion of IO partitions, and specifies IO authorization and properties. Then we successively refine the abstract model to obtain lower layer models that apply to real commodity IO hardware, IO kernels, and TEs. These lower layer models both add IO hardware details and extend model applicability to all other IO kernels. For example, concrete models add hardware authorization capabilities and specific IO separation policies. And the kernel designs add details of different device classes. And the kernel implementations add details of device registers and data structures. The implementation specifications can then automatically generate code of running IO kernels. So why does one need 3 refinement layers? The concrete models are needed because they could be general for multiple IO kernels. For example, the concrete model shown here is general for various on-demand IO separation kernels, including WinP kernel and GPU separation kernel. The kernel design models are needed because they enable early discovery of kernel design vulnerabilities, and they allow kernel composition of different device types and significantly reduce code composition proof effort. And they enable kernel design reuse between similar device types. For example, an I/O kernel of USB 3 is similar with the one of USB 2. The abstract I/O separation model can also be refined to separation kernels and commodity OS kernels, as informally discussed in our paper. So due to time limitations, I'll only illustrate the abstract I/O separation model in the next few slides, and then conclude the talk. The I/O separation model consists of 3 I/O components: subjects, objects, and partitions. Subjects consist of drivers and devices. The figure on the right shows the mappings from real drivers and devices to I/O components in the model. Objects consist of data objects, function descriptors, and transfer descriptors. Data objects store devices' input and output data, like the frame buffers in the figure. Function descriptors define configurations of device functions other than I/O transfers, like the power control register. Transfer descriptors define direct I/O transfers to be issued by devices, like the frame buffer base register defines a read to a data object. The subjects and objects belong to different partitions. Thus, I/O separation is defined as no I/O transfers can cross a partition and no mutable objects can be reused in a new partition. However, I/O hardware with inadequate transfer authorization poses a challenge in authorizing indirect transfers by devices. That is, once drivers write to TDs to initiate indirect transfers, I/O hardware cannot prevent these transfers from crossing partitions. To prevent such transfers, the model calculates a transitive closure of TD state whenever a driver modifies a TD. Then the model checks that the transitive closure does not include cross-partition transfers. The bottom figure shows the TD state right after the write driver writes to the TDI of device I. The new TDI defines a direct transfer to the TDH of device H. The computation discovers that the leftmost TD state enables a direct write from device I to TDH. This write results in a new TD state and modifies TDH. Though the new TDH defines a cross-partition transfer to TDJ, the algorithm has not discovered it yet. Then the computation discovers that the middle TD state enables a direct write from device H to TDJ. Now the algorithm discovers an unauthorized transfer in the transitive closure. Thus, the model must deny the write driver I from writing the device I, because this write could lead to indirect cross-partition transfers. The I/O separation model defines 12 operations in total, 4 operations for driver device read and write, 2 operations for empty partition create and destroy, and 6 operations for subjects, objects, activation, and deactivation. In summary, we defined an I/O separation model that can be applied to different I/O hardware designs, I/O kernels, and TEEs. We specified and verified the WinP kernel's design and implementation. This specification helped us to discover vulnerabilities in the original WinP kernel. The overall level of effort is 4.5 Poden years, in which 2.5 Poden years are for sound WinP kernel design and implementation. And the models can be reused for future I/O kernel development. So reusing the abstract model can save about 1 per year, and reusing both the abstract and the concrete model can save about 2 per years, and reusing existing lemmas and proof structure can save about a half per year. So that's all. Thank you.